Hello, I am Sayan Ghosh from Saha Institute of Nuclear Physics, HBNI, Kolkata, India, and I shall talk upon measurements and simulation of background radiation for rare event search experiments at an underground laboratory. First, I'll discuss the motivation for our work, and then I'll present the gamma background measurements and simulation for shielding with lead. Then I'll briefly describe the cosmic neon background experimental measurements and the simulation, and then the neutron background measurements and separate simulations for radiogenic neutron and cosmogenic neutrons, and I'll compare our results with other labs and finally conclude. Now, rare event searches like direct dark matter search, neutrino-less double beta decay, etc. look for extremely small signals, and this translates to extremely low event rates. Now, accurate determination and mitigation of these backgrounds therefore become very important. And as a first step to reduce charged cosmic ray background, these experiments are set up at underground laboratories. Now, the gamma ray and the neutron background are artifacts of the radioactivity of the surrounding rock, and therefore these are irreducible and specific to the site. And in an attempt to set up a rare event search experiment in India, an underground laboratory named as Jadugora Underground Science Laboratory has been set up at a vertical depth of 555 meter, which is around 1.6 kilometer water equivalent in the state of Jharkhand in India. Now, here we present the experimental and simulation results of the gamma ray, cosmic neon and neutron background at this new experimental site. Now, the gamma background in the underground laboratory generally arises from the radioactive decay of uranium, thorium along with the elements in the nuclear decay chain, and also potassium-40, which is present in the surrounding rock. The measurements in this case was done by using a CSITL detector of 50 mm diameter and height, and the scintillation was manufactured by the Bhabha Atomic Research Center, Mumbai, and it was directly coupled to a Hamamatsu photomultiplier with the built-in ASIC board provided to which provides the bias to the PNT and the multi-channel analyzer. And the calibration was done using various known gamma ray sources, and the measurements were done both at the surface and at the underground site. Now, this is the flux of the spectrum, of the gamma ray background at both the surface and the underground laboratory. Now, we can see that up to an energy of around 2.8 MeV, the flux at both the surface and at the underground lab is almost comparable, but beyond the energy of 2.8 MeV, the flux at the underground laboratory is much reduced as compared to the results at the surface. Now, for rare event searches, we need further suppression of the gamma background, and therefore we need shielding. Now, shielding can be done, passive shielding can be done by high-Z elements such as lead, and here we use Yan4 to investigate the optimum lead thickness for the shield. And we take the geometry like this, where we have kept a cylindrical detector of the same material and shape and size as that we have used in our detector, as in the main detector we have used in the experiment, and we take a solid lead box and we shoot gamma rays on the outer surface of this lead box, and we investigate the suppression factor of the gamma flux. Now, we divide the entire gamma spectrum into all these 8 zones, and we investigate the shielding factors with varied thickness of the lead shield. And what we want to point out is that at gamma ray energies more than 3 MeV, we get a suppression factor of 10 to the power 4 for a lead thickness of 30 centimeter, and below this energy range, the suppression factors are higher. Now, for the muon background measurement, we use 4 plastic scintillators coupled to photomultipliers by optical fiber, and we use it in the operated in the four-fold coincidence method mode, and the overall effective efficiency is at 97.04%. Now, one important aspect of determining this muon flux is that these muons, while interacting with the surrounding rock, produce neutrons, and these neutrons are in the energy range of a few MeV to 100 GeVs, and these neutrons mimic the WIMP-like signals, and this result becomes important for further simulation. Now we operate this detector at the surface. This is the energy deposition spectrum, which has a Landau-like feature, and we take the entire detector setup to the underground and operate it for over 1100 hours with the same electronic configuration as that used at the surface. This is the energy deposition spectrum, and we can see that there is a background riding on the Landau-like feature. Now we find that this background feature is the same as the profile that is generated from the gamma response of the detector, which was found out by using a sodium-22 source. And this sodium-22 source response profile is further used to fit this background, and after background subtraction, the flux, experimentally determined flux, comes out to be 2.257 into 10 to the power minus 7 per centimeter square per second. Now in the simulation, we generate muons on this 3 cross 3 square kilometer surface using Geyser's parametrization, and we account for the terrain information of this surface from Google Earth Pro. We propagate these muons through 555 meters of rock, and we compute the flux at the underground site. And this is the energy spectrum of the muons at the underground site, and this is the zenith angle distribution at the underground site, where the exponent to the cos theta fit is 3.756, and the average energy of the muons is around 186 GeV, and the vertical intensity of the muons obtained from this zenith angle fit is 1.558 into 10 to the power minus 7 per centimeter square per second per steradian. Now, in order to match this simulation result with our experimental determinations, we need to account for the geometry and the solid angle coverage of the detector. We account for all that by using this numerical integration, where we account for the fact that for different zenith angle of the muons, the azimuthal coverage from the detector side will be different, and therefore the phi mean and phi max. And we also employ a second method, which is basically based on a Monte Carlo, where we generate muons on the top surface of the top detector and propagate them using the zenith angle and azimuthal distributions, and we check for successful fourfold coincidence. Now we can see that from the Monte Carlo and the numerical analysis match quite well, and after accounting for all this, the simulated flux as seen by the detector would be 2.051 into 10 to the power minus 7 per centimeter square per second. Now this is a very good agreement with the experimental determinations. Now neutrons are generated from the alpine reactions from the decay of uranium-238, thorium-232 and their decay remnants, and also the spontaneous fission of these in the surrounding rock. Now the experimental measurement was done using a pressurized helium-4 detector manufactured by the Arctic's Radiation Detectors, Switzerland. This is basically a 600 millimeter long cylinder with an inner diameter of 65 millimeter, where the helium is kept at around 155 to 180 bars pressure. Now fast neutrons will give rise to nuclear recoils, and these recoils will deposit energy into the medium, giving rise to scintillation light in the VUV region. There is a lithium coating in the inner walls of this detector, which basically imparts thermal neutron sensitivity, and the low number of electrons in the helium-4 decreases the sensitivity to gamma rays. Now the N-gamma and thermal to fast neutron discrimination was done by pulse shape discrimination based on a time over threshold TOT analysis, and this TOT analysis was integrated into the electronics board, which was fit to the detector. And this is the detector that we have used, this is the TOT spectrum with the californium and cesium source. The first region is for the gamma, the second region is for the fast neutrons, and finally the thermal neutrons. And this parameter cuts based on the TOT parameter are provided by the manufacturer itself. Now we have again operated this detector at the underground and surface laboratories, and we find that the flux of neutrons within the energy range of less than 10 MeV, around 1.6 3 into 10 to the power minus 4 per centimeter square per second. Now for the simulation, we modeled the underground laboratory, which is a room of this dimension, as a hemisphere volume with radius 2.2 meter, and we place a detector volume, a cylindrical detector volume of the same size and shape as that we used for the neutron detection experiment, and we considered this rock shell around it and also rocks in the floor. This is at this bottom left corner. We show the neutron spectrum which would be generated from the radioactivity and the alpha and reactions in the rock, and we use this spectrum to generate muons inside this rock shell and also at the floor, and propagate them isotropically. Now these neutrons will undergo inelastic or elastic processes, and finally some of these neutrons will enter the lab space and hit the detector. Not only that, these neutrons may again, after coming into the lab, may hit the surrounding wall or the floor and be backscattered into the lab and hit the detector. So these backscattering effect was also taken into account separately. Now this is, after taking all that into account, this is the final energy spectrum of the radiogenic neutrons. You can see that it is within the energy range of 10 MeV, and the neutron flux is, after including the backscattering effect, was found to be 2.61 into 10 to the power minus 4 per centimeter square per second. And this is less than the flux determined in the experimental measurement. One reason is that the low energy cutoff for the thermal neutron sensitivity, and also the indeterminate high threshold cutoff for the thermal and the epithermal neutrons in the detector, which would not give rise to N-alpha reactions in the lithium in the detector. But in our simulation, we consider zero threshold, and therefore we take into account all thermal and epithermal neutrons. Finally, for the cosmogenic simulation, we generate muons following the energy and zenith angle distributions obtained from the simulation on the outer surface of the hemispherical rock shell, and the neutrons that are generated due to the interaction of the muons will again be scattered in all directions and again give rise to all the backscattering effects that I have discussed previously and hit the detector geometry. Now we found that a thickness of 200 centimeter of rock around the hemispherical lab would be an optimum choice for determining the cosmogenic neutron flux. This is the cosmogenic neutron spectrum that at the detector, and this is the fit function that we have used, which is obtained from this reference, and these are the best fit parameters. And the flux of the cosmogenic neutrons at the detector was found to be 5.661 into 10 to the power minus 8 per centimeter square per second. Now the radiogenic flux, as discussed before, is very specific to the underground site because it depends on the radioactivity and the rock composition of the surrounding walls and the rocks. But the muon flux and the cosmogenic neutron flux is something that is dependent on the vertical depth of the lab. Therefore, we compare our simulation results of the muon flux and the cosmogenic neutron flux with the results from other laboratories, and we found at different depths, and we find that our simulation results agree well with the global fits, which is obtained from this Mayenheim paper. Finally, to conclude, we have done the various background measurements at this new underground site. The gamma ray background was measured, and future plans of passive shielding was investigated and optimized during Geon force simulation. The cosmic muon background and the neutron background were also measured at this underground site. The muon Geon force simulation with results agreed well with the cosmic muon flux determination, and in the simulation we found that the backscattering of the neutrons had significant effect on the radiogenic and cosmogenic neutron fluxes. And finally, the cosmic muon and the cosmogenic neutron fluxes obtained from the experiment and simulation matched well with the data from other underground laboratories at different depths and agreed well with the global fits. Thank you. That is all from my end.